I'm Dr. Henrik Schoenefeldt from the School of Architecture here at the University of Kent. And my background is in sustainable architecture, and I have a particular interest in the sustainability aspects of heritage buildings and the history of environmental design. And I'm currently on a full-time secondment to the Houses of Parliament to lead a research project into the historic ventilation system of the Houses of Parliament, which was at the time a highly innovative system. And today I would like to talk about the environmental thinking behind the building, in particular how it might start us thinking about how we practice today in sustainable architecture. The Palace of Westminster, also known as the Houses of Parliament, was a major site for experimentation with environmental technology for over 100 years, until the original ventilation system and climate control system became redundant and was replaced with a more modern mechanical ventilation system, in some places including air conditioning. Starting in the 1930s, members and peers dismissed the original Victorian system as primitive, antiquated and ineffective. The Palace of Westminster is currently facing a major refurbishment program, and the renewal of the existing building services represent one of the greatest and possibly urgent challenges. This has been highlighted by a pre-feasibility study from 2012 and in a report of the Joint Select Committee of the House of Lords and Commons published in 2016. The current services, however, are largely post-war refits, while the Victorian infrastructure lays dormant within its fabric. The principle underlying its design, although constrained by technology, design tool and scientific understanding of its time, have surprisingly close resemblance to those deployed in modern sustainable architecture. Examples of modern buildings using similar principles are UCL Schools for Eastern European and Slavonic Studies in Bloomsbury, or the Everman Theatre in Liverpool. In this talk, I would like to explore the process underlying the design of the original system, examining how it was shaped by early environmental thought, including concerns about energy efficiency, air pollution, or the comfort of users. The process itself of developing the system preceded the stage when the original design for the palace was developed. The current Palace of Westminster was indeed erected after the original medieval palace was destroyed through a large fire in 1834. Its destruction drove Parliament to undertake an extensive investigation into the requirement of a modern, purpose-built Parliament building, in which the challenges of providing adequate ventilation, lighting or acoustics received significant attention. The House of Commons appointed a separate select committee to investigate modern technical solutions that could be applied to the new palace. It consulted various leading experts. This included the Scottish physician David Boswell-Reid, who presented a hypothetical scheme for a debating chamber involving the use of large chimneys to drive the ventilation. Concerned about the level of atmospheric pollution, he proposed a completely sealed chamber. Instead of using operable windows, the air was introduced centrally through tall towers, filtered and conditioned at basement level, and finally admitted into the debating chamber itself through a perforated floor. The hot air was extracted through a panelled ceiling, which was connected to a second tower with coke fire at its base. The convection produced by the heat provided the power to maintain the airflow without reliance on mechanical fans. Although the Select Committee did not recommend any particular scheme to be applied to the new palace, Reid was given the opportunity to experimentally verify the viability of his ideas. Indeed, it took 5 years until Reid was formally appointed to apply his principles to Charles Barry and Augustus Pugin's architectural scheme. First experiments were undertaken in physical models of his hypothetical chamber, which were erected at Reed's private teaching laboratory in Edinburgh. This model was used to explore how far adequate ventilation and comfortable climate conditions could be achieved inside a completely sealed space, in particular when it was highly crowded and at night when the chamber was illuminated with gas lights. In this model, which is shown in these historic illustrations, the indoor climate was carefully controlled, so the supply of conditioned air. What was critical about this experiment is that Reed's inquiries were strongly shaped by his medical background. Alongside addressing key technical questions, the inquiries were primarily concerned with the state of the indoor climate, air quality, and its effect on occupants. These experiments had their origins in earlier physiological research into the impact of climates and air quality, which Reed had undertaken, first whilst being employed as a lecturer of chemistry at the University of Edinburgh, and after 1832 in his private laboratory. Detailed accounts of these studies were given in two of his books, Illustrations of the Theory and Practice of Ventilation from 1844, and The Ventilation in American Dwellings, issued in 1858, and in several of his lectures. And these studies, volunteers having been exposed to atmospheric conditions of various qualities, were interviewed to determine how they had affected concentration, appetite, or physical well-being. Aiming to provide design with a stronger empirical foundation, Reed used similar methods to empirically evaluate and refine the design of ventilation from an occupant perspective. In lectures entitled Progress of Architecture from 1856 and The Revision of Architecture in Connection with the Useful Art from 1855, Reed reported of experimental rooms that he had erected in his laboratory to test ways of diffusing air currents using different configuration of perforated walls, floors, or ceilings. Volunteers were placed inside these rooms to provide feedback on the thermal sensation produced by incoming air currents and how these were affected by changes in the direction, temperature, humidity, or velocity. This research represents an early example of thermal comfort study, which did not emerge as a formal field of scientific research until the 20th century. Tests, however, were continued, this time under real-life conditions, in two temporary debating chambers. In these drawings, we can see a reconstruction that I have produced of the original temporary House of Commons chamber in which Reed undertook his first experiments with members. These had been erected after the fire to decant Parliament into provisional accommodation into the new palace was completed. It was used for field studies on ventilation, climate control, and artificial lighting, and members were involved directly in the process of evaluating and refining technological solutions. From 1835 until 1851, Reed convened extensive experimental inquiries covering both technical and human factors of ventilation. He developed a sophisticated method of monitoring, which, similar to modern post-occupancy evaluations, combined the recording of physical measurements with the gathering of subjective feedback from members. During every sitting, the indoor climate and external weather conditions and attendance were recorded in logbooks at hourly intervals. His objective was to conceive an intelligent system that could respond to the variableness of weather, feedback from members, or significant fluctuations in the number of members sitting. The latter could change from an empty chamber with just 50 members to 800 during an important debate. In contrast to modern notions of intelligent buildings, which are associated with computerized controls and sensors, the Victorian system had to be implemented entirely manually by staff working the ventilation system. Here we got an example of data that was collected during one of the sitting in May 1837. So measured data, both referring to temperature and the number of members sitting. In addition to this, the logbook contained a lot of quotes referring to members' experiences. So the review of this personal feedback enabled actually attendants working the ventilations to directly respond to members' experience. Being a psychological state, thermal comfort was not directly measurable. Through scientific instruments, it required qualitative methods, which Reed noted during interview in 1834 allowed gathering information as to the ever-changing feelings of members, of which no one can possibly judge but themselves. To address this, he actually introduced a sophisticated monitoring regime that allowed to systematically respond to members and to collect data. As the perception of climates and air purity is highly subjective, feedback was often conflicting and had to be moderated before instruction for change in climate was sent to the attendants. The role of the moderator was held by the Sergeant-at-Arms, at times by the Speaker of the House of Commons. William Gossett, who was the Sergeant-at-Arms at the time, described his experience in 1839. Sometimes members come to me and say, the house is very hot or very cold. I look at the thermometer and see if so, for different people have different feelings with regards to temperature. People come in very hot and say how cold the house strikes. And another man says, I have been sitting here for half an hour and I'm in fever. And if I see the thermometer are too high or too low, I give directions accordingly. This process of collecting and processing personal feedback from members was introduced first to inform the day-to-day operation of the ventilation, and second, to improve the design of the system from a thermal comfort and air quality perspective. Reed used the collected data to determine climatic condition at which a majority MPs would feel comfortable. In 1844, he wrote that as far as I've been able to observe, a temperature of 65 degrees Fahrenheit with an atmosphere moving in very gently stream so as not to be perceptible is the most agreeable in rooms that are not overcrowded. Referring to atmospheric humidity, Reed reported in 1852 that when there is a difference between 5 degrees Fahrenheit between the dry thermometer and the wet bulb thermometer next to it, I have the least number of complaints. In the temporary House of Lords, Reed trialed an alternative approach. And this system was introduced 2 years after he first introduced a system in the Commons. And this alternative approach, he explored how far user satisfaction could actually be increased by creating microclimates in different areas of the chamber. Reed took this concept another step further in his permanent House of Commons by providing every bench with a separate air supply. It was a more complex and sophisticated system, to which he hoped to respond more effectively to members' experience. And here we've got a drawing that I produced to reconstruct the original Reed system that was in use from 1852 until 1854. It is to be noted that in modern methods, such as building use studies, standardized surveys are used, asking occupants to rate their experience of environmental condition on sliding scales. In contrast to modern post-occupancy evaluation, however, the engagement with user in Parliament was ongoing, as it was part of the day-to-day routine. The practice of collecting measurements alongside the collection of occupant feedback was followed for over 90 years. In the House of Commons, for instance, Reed's method was used until 1941, in the House of Lords until the 1960s. This purely experimental phase ended in 1940, when Reed was formally appointed to design the ventilation system for the actual Palace of Westminster. This represented a major shift, both in terms of the scale and complexity. As early as 1839, Reed himself admitted the risk of applying his principles, hitherto only tested inside small structures, to a building of such scale. The viability of his approach were interviewed by two select committees in 1841 and 1842, before it was formally approved by Parliament. The committee, however, insisted on including a contingency plan, a backup system that could be deployed in case Reed's principles failed in practice. Moreover, the existing architectural plans produced by Charles Barry's team, which included the architects Augustus Pugin, had to be adapted to accommodate the infrastructure required for his system. It required Reed to work as a scientist within a larger team composed of architects, engineers, and draftsmen. Reed proposed to draw the fresh air from the top of the Clock Tower and the Victoria Tower, arguing that air was less polluted at high altitude than at ground level. This assumption would be later disproven by scientific studies undertaken in the 1880s. The shaft inside the two towers were linked to a central air chamber at basement level through large passages. Valves were provided to enable staff to switch the supply from one shaft to the other, depending on the relative severity of air pollution on opposite ends of the site. The hot air was to be extracted through a third tower, which was not part of Barry's original design, but was added specifically for ventilation purposes. It was a large stone spire added above central lobby. The objective was to use as far as possible waste heat to drive the ventilation. By minimizing the reliance on coke fires or steam-powered fans, he aimed to reduce the running costs. The convection in the shaft was to be sustained through heat from people, kitchen, gas lights, or smoke. An extensive network of smoke channel was introduced at roof level to convey smoke from boiler furnaces and several hundred fireplaces into the central tower. This system did not operate entirely on mechanical aids. The fresh air, for instance, was distributed through the basement by means of a large steam-powered fan. And here we got a plan of the basement showing the extensive network of air passages through which the fresh air was distributed with the aid of these fans. Integrating a highly complicated ventilation system within Charles Barry's architecture scheme, however, was a major challenge. The large internal spaces required for the movement and conditioning of air affect many aspects of the building. This included its construction, architectural form, fire safety, or interior layout. These difficulties were further accentuated by difficulties with successfully integrating a scientist within the larger design team. Being neither an engineer nor an architect, he relied on the skills of engineers and draftsmen working in Barry's office to realize this concept at a technical level. The original project correspondence illuminates the roles and responsibility of the building scientists. Working alongside a team of architects and engineers was not clearly defined or understood. Serious difficulties with achieving effective collaboration were encountered, largely due to the absence of a methodological framework by which the knowledge and skills of the scientists could be effectively integrated into the cross-disciplinary design process. This diagram here illustrates how the communication within the design team was structured. The issues caused, indeed, serious delays, and working practices were reviewed by a select committee in both houses, first in 1844 and again in 1846. To the risk of further delays, the Lords finally voted to remove Reed from the team working on the design of their chamber. His responsibility for ventilation was subsequently confined to the debating chamber of the lobbies and chamber of the House of Commons, and this only accounted for a very small part of the palace. The responsibility for completing the ventilation of the House of Lords area and the riverfront were transferred to Charles Barry's team. The architect thereby regained full control over all aspects of the design, including the more technical aspects that had previously been delegated to a specialist. This political decision also led to a significant change in the design of the system, a rather strategic change. After 1846, the House of Commons system was physically separated from Barry's system through walls inserted at basement and roof level. It marked the boundary between Reed and Barry's territory, which we can see here in this floor plan, showing the arrangement that were adopted after responsibility were split between Reed and Barry. And here we got a close-up of the central chamber showing the diagonal wall inserted to separate between the Commons and Lords air supply network. The fundamental idea of using the central tower as a principal ventilation shaft for the entire palace was also discarded. It was replaced by a decentralized approach to stack ventilation. The network was subdivided into multiple smaller systems, each supplied with a separate ventilation shaft. The House of Lords, of which I'm showing a cross-section on this slide, for instance, became an independent system that was provided with a small stone shaft. The central tower, although reduced in size, was retained. It is still one of the largest towers, but it was denoted to the role of a local ventilation shaft. The turrets, which were introduced gradually between 1846, which we can see on this slide, resulted in another significant transformation to the exterior architecture, driven by ventilation requirements. The iconic picturesque roofscape of the palace was therefore the accidental outcome of a strategic change in the organization of the ventilation. After finally moving from the temporary facilities into the new palace, when it was completed, members of both houses continued to act as design critics, critical building users who used complaints to drive efforts in improving the design. The original system did not succeed in satisfying members' expectations. Between 1852 and 1854, the House of Commons and House of Lords appointed indeed several select committees to review the system's performance in both chambers. This involved interviews with occupants, as well as scientific studies undertaken by external consultants. Despite several modifications, the issue was never fully resolved. And in response to increasing pressure from members, the system, both houses, was substantially remodeled from the mid-1850s, following a different principle. Alterations to the houses, however, did not end here. The system was not static, but subject to a continual process of technical refinement that lasted 100 years. It was underpinned by new insight gained through scientific studies, technical experiment, and through direct experience accumulated by operating staff. The system's performance was re-examined by several generations of scientists and engineers addressing issues such as thermal comfort, infiltration of external air pollution, or the problems of cooling during summer. Largely due to the absence of reliable methods of calculating or simulating performance, which is available to modern engineers, it had to be refined gradually through an iterative process of trial and error. The system also evolved in response to environmental conditions that had not been fully anticipated in the original design. This includes the level of cooling during exceptionally hot weather, or increasing the level of atmospheric pollution Starting in 1860s, for instance, the House of Commons was provided with a second air supply and a special air filter, fan and ice cooling system. Here we got a slide showing a few images relating to scientific studies that were undertaken within the chamber over its lifetime. Most of the inquiries indeed were initiated and coordinated by parliamentarians. Parliament appointed numerous select committees to coordinate scientific inquiries into building services. The most extensive and systematic attempt to refine the system was undertaken in the first 4 decades of the 20th century, exploiting the more advanced methods that had become available, including, amongst other, microbiological and chemical analysis of air purity. The select committees were appointed in 1902, 1905, and again in 1813 and 14 to coordinate the re-examination and improvement of the existing building services. These committees nominated teams of scientific researchers to undertake studies requiring highly specialist skills and knowledge, such as quality studies involving microbiological and chemical methods of analysis, fluid dynamic simulation using physical models of the chamber, or application of new instruments for studying the physiological effects of internal air currents, temperature or humidity. After 1914, the responsibility for coordinating the continuation of scientific studies was referred to the Office of Works, which collaborated with scientists from the National Physical Laboratory, the Government Chemist, and the Medical Research Council for over 25 years. Over this period, it was that the first tentative inquiry into the possibility of replacing the original system from the Victorian era with a modern air conditioning system. In the House of Commons, the inquiries ended in 1841, rather abruptly, when the original chamber was destroyed by the Luftwaffe. It was subsequently rebuilt, and although the interior was remodeled on the historic chamber, it was incorporated a modern mechanical and air conditioning system. The House of Lords, in contrast, survived the war relatively unscathed, and the original Victorian system remained in use until 1966, before it was replaced with air conditioning. Here in the slide we can see a few of the technical modifications that were done, including the remodeling of the interior of the House of Lords for the air conditioning. In the design of this air conditioning system, similar to Reed in the mid-19th century, trials were undertaken inside the chamber involving the Lords directly in assessing its performance from a user experience perspective. As such, it could be concluded that the palace has always remained an experimental building, offering an arena of technical investigation for over 100 years. I thank you for coming to hear my lecture.